All right, let's take a look at example problem 9. So we're told ammonia is heated under constant pressure of 5 bars from 0 degrees C to 200 degrees C. Determine the amount of heat, and additional information is given below. So the key here is this heated under constant pressure, right? So as an aside, right, my first law energy balance is delta U, which is U2 minus U1, is equal to Q plus W. We're not told anything about shaft work, so if we assume that the only work we have is via boundary work, then W is equal to the negative integral of P dV from my initial to my final state. But if pressure is held constant, I can bring out P, and it's the integral from 1 to 2 dV, which is negative P V2 minus V1. Okay, so if I were to solve my energy balance for Q, Q is delta U minus W, which is U2 minus U1, okay, plus P V2 minus V1. If we expand and collect terms, we get Q is equal to U2 plus P V2 minus U1. So that minus is captured there, plus PV1. Okay, U and V are both state functions, all right, which leads to the creation of a new state function called enthalpy. Okay, H2 and H1. Okay, so our first law of balance reduces to Q is equal to H2 minus H1, right, or just delta H. Okay, so for a constant pressure process, all right, we get that Q is equal to delta H. All right, so now coming back to the problem at hand, all right, there's a couple of caveats involved in this one. So we're told that ammonia is heated under constant pressure 5 bars from 0 degrees C to 200 degrees C. All right, determine the amount of heat. All right, so we're already thinking Q is equal to delta H. So additional information is given below. So at 5 bar, we're told that Tsat is equal to 4.14 degrees C. So what that tells us is at 5 bars, when our temperature is below 4.14 degrees C, we have a liquid. When our temperature is greater than 4.14 degrees C, we have a vapor. Okay. All right, we're given heat capacity of liquid and vapor. Okay, and remember, the key of that is if we assume that Cp is constant, which we can assume here, all right, we would have that, just to use some shorthand notation, that delta H, right, is going to be a Cp delta T, right, depending on if I have a liquid or vapor. And then delta H, vaporization, will give me the change in enthalpy in going from a liquid to a vapor, right, or negative would correspond to vapor to liquid. All right. So, okay, I'm going to need to calculate 3 different terms. All right, so when I think about Q for the process, okay, first I'm going to have a delta H, okay, in a liquid phase. All right, and so if going from, I'll call it some T1 to Tsat, all right, my saturation temperature. Okay, then I'm going to have to account for the change in enthalpy of transitioning from a liquid to a vapor. And then I'm going to have this change in enthalpy in the vapor phase of going from my saturation temperature to my final temperature of interest. Okay, where that, right, is T2. All right, so Q then, okay, assuming we have these constant heat capacities, or heat capacity is constant, this will be the heat capacity of the liquid times my final state minus my initial state plus delta H vaporization plus, assuming constant heat capacity, final state minus initial state. Okay. Now when it comes to temperature, we can use degree C here because we're dealing with delta T's. So difference in degree C is equivalent to difference in Kelvin. Okay. So T sat is 4.14. So let's make a note. T1 was 0 degrees C. T sat is 4.14 degrees C. Our final temperature is 200 degrees C. And then our heat capacity data is given up here. Okay. So, and just to keep track of units, delta H of vaporization is in kilojoules per mole. My heat capacities are just joules per mole Kelvin. So again, my delta T, I could keep that in degree C because a change in temperature in degree C is equivalent to change in temperature in Kelvin. Temperature in Kelvin is just temperature in degree C plus 273.15. So since it's just a shift, if you will, that conversion factor would cancel out of the difference. But what I need to keep track of is this is joules. So either I need to multiply my enthalpy of vaporization by 1,000 or divide these by 1,000 so I have everything in consistent units. So what I'll probably do is I'll divide by 1,000 when I carry this out. Okay, so let me go ahead and create a new script. Okay, and so let's get all of our data in here. So I'll have T1. So T1 is 0. T2 is 200. T sat is 4.14. Okay, and again, I'm just going to leave it in degree C just because if I have differences in temperature, whether it's Kelvin or C, it's going to be exactly the same. Okay, let me get my heat capacity and enthalpy of vaporization data. So enthalpy of vaporization is 21.242. Okay, and I'm just going to make a note that the unit of energy is kilojoules. So CP liquid, 79. Okay, and I'm going to divide by 1,000. So instead of joules, I am using kilojoules. And CP vapor, 46.726. And again, I'm going to divide by 1,000 so that in terms of energy, I'm using kilojoules and not joules. All right, so then scrolling down to the bottom, all right, to calculate Q. Okay, Q is going to be equal to CP liquid times, okay, so I'm heating up my liquid from my initial state to my saturation temperature. Then once I heat it up to my saturation temperature, I'm undergoing a phase transition from liquid to vapor, and that change in enthalpy is equal to my enthalpy of vaporization. And then once I have a vapor, I'm heating up that vapor from my saturation temperature to my final temperature. All right, and so it's final minus initial. So doing that, okay, we get the Q is 30.7209. So I calculate a Q of 30.7209, and that's going to have units of kilojoules. So enthalpy of vaporization was kilojoules per mole. CP and CL I divided by 1,000, so those were in terms of kilojoules per mole Kelvin, multiplied by a delta T, which is the same if it's Kelvin or degree C. So that term is in kilojoules per mole as well. So that's 30.7209 kilojoules per mole. Okay, and that's it. So key here was calculating delta H's using heat capacity data, where here we just assumed that Cp was constant, so there was no need to integrate integral of Cp dt. If Cp is constant, just Cp times delta T. And then we also had to account for the phase change, right? And note that our total, heat, right, or total delta H is 30.7209. All right, the contribution due to enthalpy of vaporization is 21.242. Right, that's essentially 2/3 of that total value. All right, so the phase change is significant, right, and that's why we do things like sweat, right, because it takes a lot of heat to vaporize that liquid, right, and that's heat removed from my body to cause my water to evaporate. Hope that helps. We will see you in the next problem.